The origins and unique characteristics of our solar system have always been a source of fascination and intrigue for astronomers. Recent findings suggest a revolutionary idea. Billions of years ago, a foreign star ventured dangerously close to our solar system, significantly influencing its formation and evolution. This stellar visitor may have caused massive disruptions in the trajectories of celestial bodies, pulling some trans-Neptunian objects inward and hurling them into the inner solar system. Many of these objects were likely captured by gas giants, transforming them into moons. This theory not only provides insight into the formation of the solar system but also challenges our understanding of its boundaries and celestial dynamics. When we think of the solar system, we often picture it ending at Neptune, the outermost known planet. However, beyond Neptune lie two remote and extensive regions, the Kuiper belt and the Oort cloud. These areas are considered the birthplace of comets and other small celestial bodies. The Kuiper belt alone hosts thousands of trans-Neptunian objects, TNOs, yet their peculiar, eccentric orbits have long puzzled scientists. The inclined orbits of these objects, deviating significantly from the planetary plane, have remained an unsolved mystery. Fortunately, technological advancements now allow researchers to simulate and investigate these cosmic phenomena. Suzanne Fair, a researcher at the Leiden University in the Netherlands, and her team conducted over 3,000 computer simulations to uncover the reasons behind the unusual orbits of TNOs. Their findings point to the influence of a single stellar flyby as the likely cause of these eccentric paths. The study revealed that a star with approximately 0.8 solar masses passed by our solar system billions of years ago, at a distance of about 16.5 billion kilometers from the Sun. To put this into perspective, this distance is closer than the current location of the Voyager spacecrafts, which are exploring interstellar space at 20 to 24 billion kilometers from the Sun. The simulations suggest that this stellar encounter disrupted the orbits of countless TNOs. Some were ejected into interstellar space, while others were drawn inward toward the Sun. This includes objects like Sedna, a distant dwarf planet with an orbit that stretches as far as 1,000 astronomical units, AU, from the Sun. Sedna's highly eccentric orbit can be plausibly explained by the gravitational influence of the visiting star. Similarly, other objects, such as 2008 KV42 and 2011 KT19, which move in retrograde orbits, opposite the direction of planetary rotation, may also owe their peculiar paths to this stellar interaction. The Kuiper belt and Oort cloud are not sparse collections of cosmic debris but rather densely populated regions containing countless icy bodies. These regions extend far beyond Neptune's orbit, challenging the traditional view of the solar system's boundaries. While astronomers have discovered thousands of TNOs, they estimate that millions more remain hidden. The stellar flyby hypothesis provides a compelling explanation for the inclination and eccentricity of these objects' orbits, as well as the observed anomalies in their distribution. One of the most intriguing consequences of this stellar encounter is its impact on the moons of the gas giants. Traditional theories suggest that moons form alongside their planets, maintaining prograde orbits, rotating in the same direction as their planets. However, many moons of Jupiter, Saturn, Uranus, and Neptune defy this pattern. These irregular moons exhibit retrograde orbits and highly elliptical trajectories, suggesting a different origin. Astronomers believe these moons were not born alongside their host planets but were instead captured from the Kuiper belt or Oort cloud. Jupiter alone hosts 71 retrograde moons compared to only 16 prograde ones. Saturn's ratio is even more skewed, with 100 retrograde moons compared to 22 prograde ones. This disparity is also evident in the satellite systems of Uranus and Neptune. The stellar flyby theory provides a plausible explanation. As the foreign star passed through the solar system, its gravitational pull disturbed the orbits of TNOs, sending some hurtling inward. These objects were then captured by the gas giants, becoming irregular moons. Before the stellar flyby hypothesis, the migration of gas giants like Jupiter was considered a key factor in shaping the solar system. Jupiter's migration through the early solar system likely caused significant disruptions, scattering smaller celestial bodies and influencing the distribution of moons. However, the stellar flyby theory adds a new layer of complexity. The gravitational turbulence caused by the visiting star would have been immense, ejecting many TNOs outward and sending others inward. According to simulations, up to 10 million objects larger than 100 kilometers and around 10,000 objects larger than 1,000 kilometers could have been sent into the inner solar system during this event. Many of these objects were likely captured by gas giants, explaining the abundance of retrograde moons. In the Jupiter region, retrograde captures were 30 times more likely than prograde ones, while Saturn's ratio was approximately 20-1. Although many captured moons were later ejected from their orbits, enough remained to account for the irregular satellites we observe today. The idea of a stellar visitor influencing the solar system extends beyond its current structure. More than 4 billion years ago, a star with a mass between 0.5 and 1 solar masses is believed to have passed through the outer edge of the solar nebula, the cloud of gas and dust from which the Sun and planets formed. This near collision likely occurred at a distance of about 100 Australian dollars, approximately 3 times the distance from Neptune to the Sun. As the star passed through the solar nebula, it likely stripped away material from its edges, reducing the mass of the Kuiper belt to just 1% of its original value. This interaction may also explain the eccentric orbits of many TNOs, the inclination of their planes relative to the planetary plane, and the existence of 2 distinct populations of celestial bodies in the Kuiper belt. Additionally, the mass ratio between Neptune and Uranus, as well as other peculiarities of the outer solar system, can be attributed to this stellar encounter. The stellar flyby hypothesis stands out for its simplicity and explanatory power. With a single event, it resolves a wide range of mysteries, from the unusual orbits of TNOs to the origin of retrograde moons. The probability of such a close stellar encounter is estimated to be 20 to 30%, making it a plausible scenario in the chaotic environment of the early galaxy. This single event may have shaped the solar system as we know it, highlighting the profound impact of interstellar dynamics on planetary systems. While the idea of a stellar visitor reshaping the solar system is compelling, it also serves as a reminder of the interconnectedness of the cosmos. The gravitational interactions between stars and planetary systems are not isolated events but part of a larger cosmic dance that continues to shape the universe. While most are familiar with the planets of our solar system, the Kuiper belt and Oort cloud remain largely mysterious to the general public. These regions are teeming with icy celestial bodies, providing a glimpse into the early solar system. The Kuiper belt, located beyond Neptune, contains remnants of the solar nebula, while the Oort cloud forms a vast spherical shell even farther out, marking the outermost boundary of our system. The stellar flyby hypothesis suggests that these regions were significantly affected by the passing star. During its journey, the star's gravitational pull could have ejected many Kuiper belt objects, KBOs, into interstellar space, reducing the belt's mass to a fraction of its original size. Today, astronomers believe that the Kuiper belt holds only 1% of its primordial mass. The Oort cloud, thought to house billions of icy bodies, may also bear the scars of this ancient encounter. The eccentric orbits of many objects within these regions, as well as their inclined orbital planes, point to a dramatic event in the solar system's history. Objects like Sedna, with their highly elongated orbits, provide critical evidence for the stellar flyby hypothesis. Sedna's closest approach to the Sun is about 76 Australian dollars, while its farthest point reaches an astonishing 937 Australian dollars. Such an orbit is difficult to explain without invoking an external gravitational force. The stellar visitor theory neatly accounts for this anomaly, suggesting that Sedna and similar objects were perturbed during the star's flyby. Interestingly, Sedna may not be alone in this category. Astronomers have identified other distant objects with unusual orbits, such as 2012 VP-113, often referred to as Biden. These bodies might represent a previously hidden population of celestial objects that were directly influenced by the passing star. Their study could unlock further secrets about the early solar system and its interactions with neighboring stars. The notion that a visiting star played a pivotal role in shaping our solar system offers a fascinating perspective on its formation and evolution. From the eccentric orbits of trans-Neptunian objects to the peculiar distribution of retrograde moons, this single event provides answers to some of astronomy's most enduring questions. As technology advances, allowing for more detailed simulations and observations, we may uncover even more about the mysteries of our solar system and the forces that shaped it. Stay tuned to Space Lab for more intriguing insights into the cosmos. Together, let's continue to explore the extraordinary stories of our universe, uncover its hidden secrets, and marvel at the wonders that make up our celestial home. Don't forget to like, subscribe, and join our community for more captivating content.